gentlemen. I'm very impressed to see such a good turnout this early in the morning after the dinner, so thank you very much for turning out what promises to be an excellent first session for the second day of EIMR. The presentations in this session are loosely themed around ecological and environmental modelling, and I think what they have in common is that they're taking real-world observations and knowledge and using that in models to address issues to do with impacts and sensitivities. We're making an on-time start, and I hope we'll be able to keep to time, so I'd ask speakers to please keep to time. We'll be showing the 5-minute and the 1-minute signs, and if you could acknowledge, give me a nod to let me know if you've seen those. Okay, we'll move straight on then to start with Andrew Guerin, who's going to tell us about salmon movements based on historical tagging data. Andrew, where are you? Thank you, Andrew.
Thanks, Mike. The Atlantic salmon is an anadromous species, which means that they hatch in fresh water where they remain for a period of time, after which they migrate out into the sea for the marine phase of their life cycle, where they spend a further period of time feeding and growing before they return to their natal rivers to spawn. And unfortunately, salmon are under threat from a range of anthropogenic impacts, both in their freshwater and in the marine environment. And consequently, populations have been in decline on both sides of the North Atlantic for some time. One new development that potentially is an additional threat to Atlantic salmon is the developing marine renewables industry, mainly offshore wind wave and tidal. Now, if we're to understand the potential impacts on salmon populations, we need to understand the possible effects of device encounters on individual fish, but we also need to get an idea of how likely fish are to encounter devices or arrays of devices in the first place. And if we take the example of the Pentland Firth, we could maybe think of this as a two-stage process. Firstly, thinking about how many fish pass through the Pentland Firth as a whole, or and this could equally apply to other similar areas. And then we need to think about how many fish pass through the actual specific locations in which arrays are likely to be developed. And today, I'm going to mainly be thinking about this first aspect, thinking about how many pass through the Pentland Firth as a whole. So we can think crudely of the return migration of adult Atlantic salmon as being divided into three phases. Firstly, a kind of an open ocean phase, where they return from their marine feeding grounds to the coasts of the UK and Scotland and Ireland. Followed by a kind of a crudely what could be thought of as a coastal phase, where they move around the Scottish and UK coast seeking their home rivers, and then finally they migrate up their home rivers in search of spawning sites. And again today the main focus is going to be on this kind of approximately coastal phase. Now I want, rather than kind of embarking on a complicated modelling exercise involving hydrodynamic and behavioural modelling, I wanted to see if there was a simple way to represent a very simple way to represent the movement of salmon around Scotland's coasts. Scotland is divided into 109 salmon fishery districts, for which catch and effort statistics have been recorded for some time. Historically, fish have been caught in coastal fixed-engine net fisheries, but also in rivers by net and cobble fisheries and by recreational anglers. Now, if we make an assumption that once the fish arrive at the coast of Scotland, they then follow the coast, passing through each district in sequence as they search for their home rivers, then we can represent the coast of Scotland in a very simple way as a linear series of cells, and then with a second parallel series of cells to represent the home rivers that the fish might move into. So I coded this simple model using the NetLogo program. Virtual fish can be placed into the coastal waters of any fishery district in Scotland. When the fish are placed in the model, they're given a home river ID. This is just represents the river from which they were spawned, and therefore the river that they're trying to return to in order to spawn themselves. And the home river IDs are assigned in proportion to some measure of relative productivity of the rivers of each district, such that larger river systems, such as the big ones on the east coast here, contribute more to the overall population of model fish arriving from the North Atlantic. So at each time step in the model, if fish are in the coastal waters adjacent to their home river, they have a 50% chance that they figure out that they've reached their home river and move up into the river. Otherwise, if they're not in there adjacent to their home river, they have a 15% chance that they're able to determine which direction they need to move in to get back to their home river. And if they fail that 15% probability chance, they then will move randomly either left or right along the model world. And additionally, at each time step, any fish in coastal waters have a fixed probability of being captured in coastal net fisheries. So for the first runs, I put 141 fish just off the Inchard district, which is marked by a star here. The model runs until all fish are either captured in a coastal fishery or successfully returned to their home river. The model outputs the final positions of all fish, and then I repeated this 10 times. And this is what the output looks like. You can see the fish dispersing outwards from the release point and being captured in declining numbers in the coastal fisheries, while the picture for river returns is a bit more complicated because it's driven by not only the distance that fish have to travel from the release point to get to their home rivers, and therefore the risk of being captured in a coastal fishery before they get home, but also the relative proportions of fish coming from each river in the model. So that's interesting, but does it necessarily bear any resemblance to the movements of fish in the real world? Well, fortunately in Scotland we have access to a kind of a historical archive of some tagging experiments that were carried out over the last 100 years or more. These relatively simple experiments involved a group of researchers going to a coastal netting station, tagging a lot of fish that were captured in the netting station, releasing them, and then basically waiting to see where those fish turned up, either in other coastal netting stations or in rivers. You couldn't necessarily repeat this today because the coastal fishing sector has declined, so your returns from coastal netting stations would be much smaller. And this map shows you the tagging studies that I used to look at my model. A number of these studies the results were summarised by Malcolm et al. From Marine Scotland Science in 2010. So this is what a simple output from the model looks like compared with some of the actual data. I'll just take a moment to explain these plots. The red bars represent the numbers of fish that were recaptured in the tagging district, and the green and yellow bars represent fish that have moved away from the tagging district. There's two ways of thinking about it. Either the green bars can be thought of as the numbers of fish that move left along the model world or anti-clockwise around the coast of Scotland, while the yellow bars are those fish that move right along the model world or anti-clockwise around the Scottish coast. And you can see there's for this one experiment, a reasonable correspondence between the numbers of fish going either way in the model and in the real data. Okay. So I'm going to come on and present and show a few more results from comparing the model data from a range of tagging experiments. From now on I'm going to leave out the red bar because recaptures of fish in the same location that they were tagged don't tell us very much about their movements. So again, the green bars are fish moving left along the model world or anti-clockwise around Scotland, while the yellow bars are fish moving right in the model world or clockwise around Scotland. And in all cases, the left-hand charts are the model data and the right-hand charts are the actual tagging study results. For these two studies on the northwest coast of Scotland, you can see again a reasonable correspondence between the proportions of fish moving in either direction. If we go to the Thurso tagging study, we actually see a very poor match between the model data and the real tagging study data, but this is potentially due to the fact that this tagging study had a very low recapture rate, or at least most of the fish were recaptured at the tagging site. These two experiments are quite interesting because they show here the model is predicting a largely southward movement of fish along this coast, but in actual fact the more fish in the real world were moving north along this coast. So the model again there is not matching the data from the model. The data from the tagging study. If we move along here to these two studies, you can see again the model this time is predicting a trend in the right direction, but it's getting the numbers wrong. More fish are moving east in the real study than were predicted by the model. And finally, if we move to these two studies on the east coast of Scotland, the model is now predicting predominantly northwards movement of fish, but again, it's underestimating the proportions of fish that are heading north. So, but what to take away from this is that the way the model is set up at the moment, it represents some tagging studies reasonably well, but others not very well. And if we look at a different output from the model, this time the relative numbers of fish that were captured in coastal waters compared to the numbers that are making it back to the home rivers, we can see again a similar pattern in that the model does a reasonably good job of predicting the output of some tagging studies, but a really quite poor job of predicting the output of some of the other studies. And finally, if we look in a little bit more detail at two particular studies, this time looking at the relative proportions of fish or the numbers of fish captured on the west coast of Scotland versus the north coast of Scotland and the east coast of Scotland. You can see for the spade tagging study here that the model does a reasonably decent job of predicting the outcome of the tagging study. However, the model does predict some movement of fish to the north coast and west coast of Scotland, whereas in reality, no fish were recaptured on the north coast and west coast of Scotland in this tagging study. And again, if we look at this inshore study in this respect, we can see that the model is predicting that most of the fish will go to the east coast, but in actual fact, in the actual tagging study, most of them will be recaptured on the north coast. Okay, so a few conclusions. This kind of simple individual-based model or agent-based model can represent some features of the coastal migration of returning adult salmon in Scotland, but other features and results of other tagging studies are not well reproduced. So there's a number of reasons that could be behind this. There could be some flawed assumptions that I've used in constructing the model. The simple idea of linear passage back and forth along the coast of Scotland could be simply too simple an assumption. And there's also a lot that I can do to investigate how different starting points of fish in the model might affect the results. And there are also some potential issues with the underlying data. So I said that fish have a constant, if you like, a uniform probability of being captured at each time step when they're in coastal waters. This is very likely to be wrong, as coastal fishing effort was much greater in some fishing districts than others. But the model can be modified in a number of ways to explore some of these different alternatives and to see how changes in the underlying assumptions affect the outcome of the model. So I'd just like to thank some of the people that have supported this work. I had a bit of trouble with the uploader this morning, so it's not available to be viewed and downloaded just yet, but I'll put it up later. And also I would like to thank you for coming out at this hour after the conference dinner.
Thank you, Andrew. Thank you, Andrew. You've made excellent design there, so we have time for a few questions.
Shows a 15% increase probability of fish going towards the river. Why 15?
Okay, well, I didn't have time to cover it in this presentation. I was focusing more on the results, but I did spend some time running some kind of very simple sensitivity analysis to kind of select the kind of the values that seem to work best. It seemed to be most successful at predicting the results, and the 15% probability was the kind of the best match for some of the tagging studies. Now, it might be that the 15%, if I change the 15%, it might shift it so that it works better for some studies than others.
Anybody else? And Andrew, could I ask whether the presentation we saw yesterday, based on very recent salmon tagging data, told you anything that you would like to take on board with your modelling?
Yes, yeah. The result showing that once some of the fish that Marine Scotland tagged actually did go back offshore some distance, as obviously the assumption in my model was that they wouldn't do that. So it might be that even with that assumption in, the model still works well enough But it also might be that I need to think about, well, for example, I could perhaps build another layer of cells representing the further offshore. So, I mean, yes, it's definitely something that's useful and interesting.
Thank you, Andrew.